Hey gang, and welcome to the Worksheet Solutions Walkthrough for the worksheet, Benzene Substituents, Reactions, Concepts, and Synthesis Practice. Okay gang, this is our second go around with benzene chemistry, and I apologize if some of the stuff in this unit, in your class should have been included in the first unit. I guess it depends on, who's teaching your individual course, but I'm blabbing too much. You are clearly here for extra answers based on the worksheet that you were working on. So without further ado, let's jump in. Okay, gang, to start this worksheet solutions walkthrough off, we have parts A and B of problem 1. There's parts C and D, but we'll get to that in just a second. So in these first two problems, what we're going to do here, you can see the answers in red, but what we're going to do is up top, we're going to, from 1 to 3, rank these structures from being, the weakest acid to the strongest acid. Down here, same game, but in terms of basicity. So starting up top, and funny enough, it was a little bit of a stinker. I made them just 1, 2, 3 for both. So up top here, right? Weakest to strongest acid. Now, unbelievably, right, that very, very, very initial skill we learned in jOeCHEM in terms of, evaluating strength of acids or bases, it obviously never goes away. So we have a bunch of acids here, some phenol derivatives, but what I'm gonna do is just kind of compare them as conjugate bases. So after we lose the proton up top, we can kind of check how stable these conjugate bases are, and based on their stability, the more stable they are, the stronger the acid they came from. So I think what you can see here is the groups down here are going to determine the strength of the acid. Obviously, we have a negative charge up top, and in judging these three, hopefully you can remember from your past benzene days, when we first started doing like EAS reactions, this group right here, this methoxy group, is a strong electron donating group. This methyl group over here is a weak electron donating group. It donates electron density to the ring through hyperconjugation. And then over here, remember, the atom directly attached to the benzene ring is partially positive. So this is going to be an electron withdrawing group. The reason why the donating and withdrawing characteristics of these groups matter is because that determines how stable this negative charge is through different resonance structures. For example, if I did this resonance, I now would have a negative charge right here, right next to a very strongly partially positive oxygen. And that's not a good situation, right? We'd be putting a negative charge next to something that's pretty negative itself. Again, that would also be the case here. It's not as, okay, I put the double bonds differently. It doesn't really matter. Same deal here and here, but this isn't as bad. This isn't as egregious as an offense as putting a negative formal charge next to a partial negative atom, or putting a negative charge next to something that's negative leaning, but very slightly. However, over here, we actually see where not only can put a lone pair here next to a partial positive atom, we can actually continue the resonance such that I could swing electrons here and kick electrons up onto oxygen, an atom that loves negativity. So basically, the resonance here is not as good as the resonance here, and it's certainly not as good as the resonance here. So this structure is the most stable, aka the strongest acid. This one is better than this one, so this is more stable, so that's why we get 3, 2, and then this structure comes in last place, which is 1 here. Cool. Now, moving down to weakest to strongest bases. Now, I personally like thinking of things in terms of acids. It's a bit weird when you start thinking of bases, but what we need to think about here is how good these structures are at grabbing H+, right? So for this particular problem, what I like to think of, clearly the most basic atom we have in each structure here is the nitrogen. What I like to think of is how negative is the nitrogen in each of these scenarios. The more negative it is, the stronger the density of negative charge is on it, the better the base it will be. Over here, we have 0 resonance. This nitrogen is as partially negative as it can be. There's nothing kind of taking its charge away. However, when you look over here, different story. we have resonance here. This nitrogen will be donating density to the electron, or donating electron density to the benzene ring. It doesn't have all of its negativity all the time, right? There will be structures where it looks like this. In this particular situation, whoops, it'll look like this. So it has some type of partial positivity to it. At the same time, right, we have that effect going on over here, but we also have the ability to draw resonance this way. So in terms of how basic these structures are, this nitrogen is definitely going to be the most basic because there's no resonance. It's in control of all of its negative charge all the time. There's resonance here that will take some of it away in this case. And then this situation, there's even more so because we have resonance in both directions. So least basic, second most basic, most basic. Okay, gang, we have 2 more parts to problem 1. Let's keep going. Okay, gang, to finish out problem 1, excuse me, we have parts C and D. So starting with C, we have hitting you with one more ranking question. So again, we need to rank from 1 to 3, 1 being the least, 3 being the most. And what we're ranking here is how susceptible to nucleophilic aromatic substitution. So a nucleophile coming in and attacking a benzene ring, how susceptible these structures are to NAS. So remember the key cornerstone concept here is that when you attack one of these rings, right, and do NAS, when a nucleophile comes in, let's just assume we had O-methyl, for example. When you come in and attack where a leaving group is, you do so at that carbon and you kick up a lone pair, right? And when you have substituents on an aromatic system like this, depending on what kind of substituents you have and whether they're withdrawing groups or whatnot, the negative charge could be more or less stable based on whether they're electron withdrawing or donating, as well as where they are at the ring. Are they ortho, meta, or para to the location where you're attacking? So one thing we do like is we like electron withdrawing groups, and we like them ortho, para to the attack site, to where our leaving group is. So if we take a look right up here, I'm going to erase this. If we just, for example, since we know the attack will happen, let's just say I put a lone pair right here. We actually see that where this leaving group is, we have meta and meta. And if you do the resonance, you're going to see that we actually don't get to kind of take advantage of these withdrawing groups. We don't get to have them kind of, stabilize this lone pair through resonance. So unfortunately, this is not a great situation, right? We have meta, we have EWGs, which is good, but they're meta to where our leaving group is. Now, if we move over here, now this is our good situation here, because when we have attack and this lone pair jumps up here, right? Let's just say I'll draw it right here. Not only do we get this lone pair right here, but if you expand this nitro group like this, you can actually have the resonance go all the way over here to the oxygen. So that's why the ortho-para situation is perfect. And if we actually swung the lone pair all the way around the ring, this nitro group will also participate in this resonance. So this is our best case scenario. So this is great. Over here, we actually, we have the right positioning between this EWG and our, leaving group, but we only have one group. So this is our best case scenario because we have an ortho-para, we have both an EWG or ortho and para to where we're attacking a maximum amount of resonance. That's awesome. That's why we give this the most susceptible to NAS. We give it a 3. This is great, but we only have para. So that's why it comes in second place. And this is dead last because while we have the EWGs we want, they're just not in the right position relative to where we're attacking, aka where the leaving group is. Okay, now moving down to D. I gave you a target molecule over here, and I gave you 3 potential reactions and asked you, or I'll go over here, which one would be the best type of reaction to produce this molecule over here. So there was a few things going on here. So we know A is the answer, but let me talk to you maybe about why C and B have issues. So with C, what we're trying to do here is actually an EAS reaction, right? The one thing C doesn't have in terms of the reactant is this final nitro group over there. So we're trying to put it on right here. However, right, since we have two benzene rings here, right, if we take a look at this ring over here, yes, we do have this ortho-para director, so we would go here, but this ring is slightly, or not even slightly, it's deactivated because of the presence of this electron withdrawing group, the nitro group. So if you were going to do nitration on this structure, if you actually look here, this ring has two activating groups, whereas this ring over here only has this one activating group, right? And one deactivating group. So you would realistically put a nitro group on this ring and it would direct ortho-para somewhere. So that's why this one does not work, or it wouldn't give us the best yield of this product. And then when we look at B, right, what we have going on is this would be our nucleophile, and we would be doing nucleophilic aromatic substitution, NAS, on this structure right here. However, we do have a group, a substituent para to where we're going to attack where our leaving group is, but it's an EW or an EDG, which is not good, right? Like we just saw up here, we love EWGs because through resonance, we get great stabilization. What we'll end up getting when we attack here is resonance like this, and we'll put a negative charge next door to an oxygen that is already partially negative. That's not a great situation. And then when you go up to A, the creme de la creme, we get exactly what we want. This piece is actually the nucleophile this time, and then we have our leaving group right here, and you can see we have an ortho-para. We have two EWGs, ortho-para. The resonance is going to be perfect and stabilized, which is why A is the best situation to produce that target molecule over there. Whew. Okay, gang, a lot going on in problem one. We have 4 problems total. We're diving into 2. Stick with me. Let's go. Okay, gang, rolling into problem 2, we have 8 total complete the reaction questions or reagent or provide me the reagent or the reactant or whatever. So we got 4 right here. Let's get going. So rolling into the first one. Now, this one is kind of like a little bit of phenol chemistry, and then you know me by now, I like to kind of pull back things from our past to make sure they're top of mind, because that's all fair game. Everything you've learned up to this point builds on itself, or even if it doesn't, it's still, it can pop up at any moment. So in this first problem, 4 steps, but we'll go 1 step at a time. So we have phenol, and this first step is just sodium hydride. So when, all we have is a very strong base, good acid. All we're gonna do here is have the hydride come in and deprotonate, a little acid-base reaction. So now we have, phenoxide, right? Then step 2, methyl bromide. Just really simple, SN2, right? OCH3, sorry, just trying to leave myself a lot of space. So now we have, a methoxide type of, benzene substituent. And then in 3, you can see we're gonna do a Friedel-Crafts acylation, right? So what I was trying to aim for here, right, we see we have OCH3, just to tie it over to the product, which we do see, we have the OCH3 here. This has lone pairs and donates electrons to the ring. So this is an electron donating group, an EDG, and it directs ortho-para, right? And remember, because of sterics, we're always going to put that first group. If we can put it para, we will put it para. So then we end up with this right there, because there's 2 carbons. We'll connect this carbon right here directly off of the benzene ring. Now step 4 is the curveball. 4 is going to be a Monic reaction, right? A little bit of a, switch up. Is it something that's relevant to this unit right now? No, but at this point in time, if you're watching this, you've probably got your OCHEM 2 final on the horizon. So I wanted to make it a moment where maybe you needed to look back and refresh yourself on the Monic reaction. I did do a quick little pause because I realized I missed a carbon over here, and I wanted to kind of reset over here so I could show you a little bit more of the Monic reaction. So remember, with a Monic reaction, you're gonna have 2 components, a carbonyl and an amine that will work to form an imine, but more so an iminium ion that will get attacked, right? So what that will look like is this. We have one carbon here, so I'll kind of keep the way that kind of looks like formaldehyde, and this right here. So throwback to imines, you almost make an imine, but it stops just because it's going to get attacked. And then because we're in an acidic environment, our product from 3, our intermediate, actually becomes an enol, right? Because remember, we can form enols in acidic conditions, and that's going to function as our nucleophile here. So what we got going on here is we attack the carbon right there in the iminium ion, and as a result, right, the iminium ion unfolds and we get an amine back. And then this right here will flip back to being a carbonyl, a ketone. So we're connecting this piece that I'm going to dot, which is this carbon over here, and then we're going to connect this carbon that I'm going to asterisk, which is this one over here. And you can see that asterisk carbon is attached to a nitrogen, a hydrogen, and an ethyl group, which I actually drew out. So that's the long way of this problem. Kind of started with relevant information that was recent. We used a phenol, we deprotonated it, we used it as a nucleophile. Nothing conceptually brand new to you, really, but technically. And then we did some EAS stuff from many moons ago, and then from moons ago, but not so much, but could also have been rusty or not as fresh in the mind, we did a Monic reaction. Cool. Moving on into this problem right here. I asked you for the reagents, and what we had was toluene, methylbenzene, right? Benzene with a methyl group. And all you saw was a bromine here. And this, while not the most complicated problem, could have been a little tough because, again, I'm reaching back in your past, but kind of leaning on a fresh or a newer concept, a present concept. You can just use the free radical bromination here because remember that this goes through a radical intermediate. And because that's in the benzylic position, that's a benzylic radical, this thing has tons of resonance available. It's super stable. So this is a very easy, high yield way of putting a bromine on that particular spot. Cool. Now down here, now we're kind of getting much more to the more hardcore new stuff or relevant stuff to this unit. We have this reactant right here. Sorry, gang. First step, we see H2 and PD. So maybe from our previous benzene unit, but all we're gonna do here is reduce the nitro group to be an amine. So that gives us NH2. The reason why we need, what that kind of leads us into is step 2, which is going to be diazotization, right? So what we have here as step 2, we're gonna do a lot of things here. I'm gonna kind of just erase this in place. Well, actually, I'm gonna erase this up top here too, so I have some more scratch area. Step 2, we will eventually go through and create arenadiazonium ion. It's been a minute. But remember, we won't stop here. This leaves as N2, arenadiazonium, and we get this aryl carbocation. And that is where we get attack from Br minus, and we get our product over there. Cool. And last but not least, for this particular kind of set of 4 problems, we have this right down here. And all we're going to be doing is using hydrogenation to cleave an ether bond from the benzylic position, right? So because the bond is from the benzylic position, from that benzylic carbon to this oxygen, we actually just cleave that bond straight down there. We're left with what's on the left. It eventually will become OH. And then we're just left with whatever's on the right, which is actually just methylbenzene, AKA toluene. Okay, gang, first 4 down, 4 more to go. Okay, gang, let's finish the last 4 problems in problem number 2. Okay, so in this first one we're seeing up top, I gave you the product and the reagent, and I tasked you with giving me the reactant that made the whole thing make sense. So if we take a look at this reactant, we have manganese oxide. Now manganese oxide is good for oxidizing oxidizing alcohols in the benzylic position. So if we take a look at our product, we actually just have the one carbonyl that's in a benzylic position. This alcohol is one carbon too far away. So when we're coming up with our reactant, we only need to make sure we take this carbonyl and make it, revert it back into an alcohol. Now, a slight little gotcha here is that we don't know what the stereochemistry of this alcohol was beforehand, right? So that's why I put a little squiggly line. Depending on your teacher, I would make sure to either draw both the wedged and dashed version of that stereocenter or use the squiggle, but remember, going forward, whatever stereochemistry we have here, we will lose when we get oxidized to an sp2 trigonal planar carbonyl. Okay, so little oxidation problem there with the stereochemistry gotcha. Now, the second problem right here. This does involve a Claisin rearrangement. So this one definitely, I feel like the Cope and Claisin rearrangements can be tough. But let's take this one step at a time. So in this first step, right, we have a phenol derivative. We have potassium terbutoxide. First step, we're just going to deprotonate our alcohol. So we have this right here. Second step, we have deprotonated alcohol, we have alkoxide. We're going to have SN2 occur specifically on this carbon right here. So I'm going to cheat. We'll have this. Okay? Now we get to step 3, and that's where you just see heat. Now, if you get to this position and you're looking at a structure that's aromatic, and you can kind of see a chain of 6 atoms like this, then with the oxygen embedded in, then you are primed for a Claisin rearrangement. Now, the way this rearrangement will go is as follows. Carbon number 1 is going to reach out and grab 6. This double bond has to bounce so that we don't break the octet rule. So it moves in between atoms 4 and 5. And then what's actually going to happen is the oxygen carbon bond between positions 3 and 4 is going to break, and we actually make an oxygen carbon double bond. So I'm going to keep drawing down here. We get this as our aftermath, initial aftermath. We didn't touch anything going on here at all. We have a double bond right here, and I'm going to keep my labeling 3 and 2. Position 1 actually has something entirely different going on. It's bonded to carbon, 6, which is a carbon. 6 is bonded to both 4 and 5. And we don't have anything more to draw because, oh wait, I did that backwards. Sorry about that. 5 and 4. 4 is no longer bonded to 3, but there's a double bond between 5 and 4. Oops, let's keep it black. Cool. Now, the last thing that needs to happen before we call this problem done is we disrupted the aromaticity of our ring, and that's a big energetic no-no. Nature is pretty motivated to get that back. So you can assume that there's going to be some water, and maybe I should also put some like water and H+. But you'll kind of have this situation going on where you have this get restored, and then at the same time, you will have this return back to being an alcohol. So you definitely will, do a little bit of an elimination step here to regain your aromatic system. And then in doing so, you'll have to move this bond somewhere else. It'll get protonated to make the room so that aromaticity can be restored. And that's how you end up with this monster over here. Okay? Claisin rearrangement can be a tough one. I would say hit the examples pretty hard. I know I had to. Okay, moving right along. In this middle problem right here, and I'm sorry, things are getting a little crowded. Let's draw some lines. Okay, cool, right here. So I gave you the beginning and the end, and I asked you for the reagents, the middle. Now this problem, it's deceivingly tricky in that we do have an electron donating group, and we see here we need to put a group on in a pair position. So why don't we just go ahead and do a Friedel-Crafts Acylation, call it done. The trick is that if we went ahead and threw in our acyl chloride and AlCl3, our acid chlorides are very reactive. There's a good chance that this alcohol will just straight up go ahead and do an addition elimination on this already, and we'll end up with an ester. And that's not what we want. So to get the best yield possible, we need to do a protecting group and then deprotecting thing afterwards, just to make sure we get the highest yield possible. So what I did here to make sure that could happen is I threw in T-butanol and some acid. So the very first thing is this: let's actually make an ester. Or I'm sorry, not an ester. We just make a big, bulky ether, my apologies, such that then this would be really hard to actually perform an attack on, you know, an acyl chloride if we toss it in. Then we go ahead and toss it in to actually, so one, and then for step two, that's when we actually stick this on. And then for three, we actually just deprotect we go back to the alcohol from having our ether. We just have our product, which is this and this. So a little bit of a roundabout way, but just an extra deprotecting step to really, really, really make sure that this goes the way we want it to. And maybe it's because, and just in case it's been a minute, but to show you that protecting this number one step really quickly, the way this works is this would get protonated by the acid. Then because this is a tertiary position, this leaves, you end up with a carbocation that this would then just attack. So you kind of generate a tertiary carbocation that this thing attacks, and then when you protonate this, you just unravel it. Cool. All right, and last but not least, we have a co-prearrangement. Now, I did have some steps on the actual solution to really, I'm just gonna kind of show you them again to show you this out. I highly recommend you draw these to really make it a little bit easier on your life, because they can be tough to kind of mentally see, at least for me personally. So we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have a double bond here and here. So I'm not going to leave my memory to chance. You can see we have 1, 2, 3, 4, 5, and 6. So we kind of have, and again, this rearrangement happens completely outside your benzene ring. So you can see we have, you know, this carbon not having anything, the bond to the benzene ring doesn't change. It's the atoms outside of it attached at that same position moving around themselves. So I like to kind of think of it as 6 using this bond to go ahead and grab on 1. And that kind of starts off a little bit of a chain reaction. Then 1 goes, oops, I have too many bonds. It makes this bond bounce over here to move between 2 and 3. And then because 5 kind of lost out on a bond because 6 was being a bit greedy and took it, then 5 needs something to kind of make up for that. And what happens is a cleaving of the 3 and 4 bond that bounces right over here. So again, you kind of have this circular thing going on. If we label this as 1, 2, 3, 4, 5, 6, almost maybe redundantly drawing the arrows again, we know 6 comes over here and bonds brand new to 1. This bond kicks over between 2 and 3, and it's the breakage between 3 and 4 and the double bond connecting at 4 and 5. So think of it like this. 1 is still here. Nothing changed about that. And 1 is still connected to 2 and 3. But it's at 3 that a bond was broken. But now we know there's a double bond between 2 and 3. So right over here, you know that you can draw 2 and 3 and have a double bond. The tricky part then is what else is off of 1, the carbon right off of the ring? Well, that's now 6. So we know this carbon is 6 over here. 6 is still connected to 5, and 5 is connected to 4, but by a double bond. So we know this is 5 and this is 4, and that completes everything because we know that there's no connection between 4 and 3. Whew, I don't know about y'all, but my brain is a little bit done with these rearrangements. So thanks for powering through all these problems with me, gang. For problem number 2, we have 3 and 4. Stick with me. Okay, gang, in problem 3, we have 2 parts. So let's start with A. In problem A, we are tasked with drawing this mechanism up top. And hopefully what you saw here was that we have phenol going to this product right here. And this reaction has a little bit of a name. This is the Colby reaction. So let's take a look at how the mechanism goes. So in the first step, we have phenol and we have sodium hydroxide. So all we're doing here is a little deprotonation of the alcohol off the benzene ring. So we end up with phenoxide. And then what we have next is, we usher in carbon dioxide. Carbon dioxide is double bonded to 2 oxygens. So it is extremely partially positive, very susceptible to nucleophilic attack. So what we see is we really just created an enolate right here. So what we see is electrons swing down. This carbon right here is our nucleophilic carbon. It takes control of these double bond electrons, these pi electrons, and attacks carbon, and electrons kick over. So in the result of that step, we did 2 things. We have now a carboxylate group, which is cool. But we did disrupt the aromaticity of the ring, and we will have to recover that. So we move into step 3, which really this should kind of, you can just assume that there's, H2O here as well. We protonate our carboxylate up to a carboxylic acid, but then we have to pay the piper. It's time to make sure we, do our duties and return the ring to an aromatic status. So we bring in water to deprotonate this carbon right there. We take off the proton, we swing electrons back into the ring, we restore aromaticity, and kind of in a keto-enol tautomerism like step, we also have to grab a hydrogen here, kind of going from the keto back to the enol phase, which is a bit weird. That's the opposite of what we usually do, but remember, it's all in the interest of restoring aromaticity back to the ring. So that's how the mechanism goes. Now in part B, we actually have to, it's more of a explain this phenomenon type of question. We have to account for the fact that when we subject this reactant to these conditions, why do we get 50% of meta-methylaniline? Right here, we can see a meta relationship between the methyl group and the amine, and a 50%, also result of the ortho product. What this comes down to is, it comes down to nucleophilic aromatic substitution, and it really comes down to the intermediate we go through. So we have a very, very, very basic NH2 minus in solution. What that's going to do is it's actually going to protonate the position next to our halogen right here. The reason why that's going to happen is when we have electrons right here, one thing we can do is these electrons can swing down, weirdly form a very rare triple bond benzene intermediate, a benzyne intermediate, and will eject our good leaving group. Now, once we have this is pretty unstable. It won't stay like this for long. And we have a nucleophile that can attack. Where it attacks though, accounts, that's up to chance, where this NH2 minus and where this structure collide, which is why we see, theoretically, we see a 50-50 split, because there's no difference whether we attack here and get the ortho product, or we attacked here and yield the meta product. Whew, okay gang, it's been a long walkthrough. We've done 3 questions, we have 1 left, synthesis problem, stick with me. Okay gang, problem 4, let's finish strong. Okay, so in this synthesis problem, we had to, from benzene and ethanol, synthesize this target molecule over here. Now, I feel like the crux of this problem were 2 things. One being the use of NAS and making sure you had an electron withdrawing group ortho para to make sure that that was a good NAS reaction, as well as the fact that we can remove carbons via KMNO4 oxidation, like oxidative cleavage, okay? So I'm gonna kind of just walk you back this way and even reading it forward could maybe make sense as well. So with this target structure, right, what I'm seeing is clearly we can see benzene represented because we only get to work with benzene and ethanol. I think the tricky thing might be is that we see, all the carbons right here accounted for. We have 2 carbons up here with, ethanol handy. We obviously see 2 carbons over here handy, but then we just see one weird, lonely, awkward carbon over here. So what I'm hoping makes sense is we can easily account for these two. These definitely come from ethanol. This obviously comes from benzene, but weirdly, where does that last carbon come from? And what's going to happen is we'll eventually put 2 carbons on at this position, but then we use KMNO4 to cleave it completely, leaving just a carboxylic acid, and that's how we kind of get 1 carbon right here. But anyways, getting ahead of ourselves. Starting at the end, right? If we want to take one step back from this, hopefully this makes sense. We have an electron withdrawing group right here, right? This ester, this carbon right here is partially positive. We can have electrons come out of the benzene ring. So what I'm trying to say is, if we take one step back, we could have ended on a nucleophilic aromatic substitution step. So what would be convenient is if we had eth oxide, right? If we just had ethanol deprotonated, if there was a good leaving group at this position, we could easily kind of stick this on. So one step back, I used eth oxide as my reactant, and I just used bromine right here. So bromine would be a good leaving group. Eth oxide would attack right here. We have our EWG to resonance stabilize the charge that gets created during the attack. This step works. So we kind of have like this carbon source taken care of. Now we're kind of running into the second part, right? So this was kind of this part. Check. Now follow me here. If we know that this could be a carboxylic acid at some point, we know that this is just an ester. So if we take this one step back and kind of say we tossed in ethanol and acid, we can actually get this back into that carboxylic acid form, right? Which means we could go one step back right here to say we did a KMNO4 oxidation. We know that if we have just some R group like this with hydrogens, at least one hydrogen available, whatever, then we can use KMNO4 to just literally chop the whole thing, leave 1 carbon, and make that carbon a carboxylic acid. So that's what I did in this back step. And now we can kind of even really deconstruct this, because what we have is a bromine and an alkyl group. So since this is an alkyl group right here, it would direct orthopara. If we go one step back, this could be my step to actually do bromination in an EAS fashion. If I threw Br2 and FeBr3 in, going back and I just had ethylbenzene, then this will definitely direct para. So I can take that step back. And then what I can do from here is now, here we go. We just have 2 carbons right here. I can definitely work with benzene and this to get to here. So it'd be nice if we could go back to like a Friedel-Crafts acylation. So if I go one step back, I could, say I would like to have a carbonyl at this position. Well, we have a lot of different ways you can reduce at the carbonyl, the benzylic position, carbonyl wise. I like to use H2PD. So stepping back with H2PD, that carbonyl can reappear. And now we have our, oops, shouldn't be there, sorry, my bad. Now we can actually stick this on. We can do a Friedel-Crafts acylation. I can use benzene, which is starting material, and then I can use acetyl chloride, to make this happen. And now I just need to explain where this came from. And that's easy, right? If I step it back with SOCl2, I get a carboxylic acid, and then to get that from the alcohol, just use sodium dichromate and H2SO4, good old Jones reaction to bring it on home. Gang, thank you if you're still here suffering the slings and arrows of this solutions walkthrough, you are a real one. Thank you so much for watching this video solutions walkthrough. If you were looking for answers, I'm hoping, praying you found them here. Thank you so much for being a jOeCHEMist. I hope this website, this YouTube channel is helping you conquer your way through organic chemistry. If you haven't subscribed yet, please toss a subscribe my way. And no matter what, I hope to see you all in the next video.